Today we'll be doing the integral from 0 to infinity of the natural log of x divided by x squared plus 1 dx. And to start off, we could construct f of z is the natural log of z divided by z squared plus 1. And the poles are at z equals 0, z equals I, and z equals minus I. But we're not going to worry about z equals minus I in this contour. So we have from minus r to negative epsilon, and to epsilon to r. And then we'll have this loop gamma, and its bigger loop, big gamma. And so the integral over this contour will equal the integral from minus r to minus epsilon, plus the integral over the small loop, plus the integral from epsilon to r, and plus the integral of big gamma, but this will eventually go to 0. And I'll focus on this first integral, the integral from minus r to negative epsilon of the natural log of x divided by x squared plus 1 dx. Now make a substitution. I'll let minus t equal x, so that tells us that t equals negative x, and that dt equals negative dx, so that negative dt equals dx, and t sub 1 will be positive r, and t sub 2 will be positive epsilon. So this is going to be the integral from r to epsilon of the natural log of x, which is negative t, divided by x squared will just be t squared, plus 1 dx will be negative dt. But we could rewrite this as the integral from epsilon to r of the natural log of minus 1 plus the natural log of t divided by t squared plus 1 dt. The natural log of minus 1 is I pi. And as r approaches infinity and as epsilon approaches 0, we have the integral from 0 to infinity of I pi over t squared plus 1 plus the integral from 0 to infinity of the natural log of t divided by t squared plus 1 dt. But this is exactly our goal integral, which we denote it as I. And we have to evaluate this other integral, but that's standard result will be I pi, integral from 0 to infinity of 1 over t squared plus 1 dt, which is just I pi, the arctangent of t. Evaluate from 0 to infinity, which is I pi times pi over 2, which is I pi squared over 2. So the integral from minus r to negative epsilon is just equal to I pi squared over 2 plus I. I'll finish up the board and we'll see the next integral. So we just got done showing that one of our integrals was I pi squared over 2 plus I, and I'll make the notion that as r approaches infinity, as epsilon approaches 0, this integral will just become our I as well. So the integral over contour will just be I pi squared over 2 plus I plus the integral over the small loop. And this would just become 2I plus the integral over this small loop. And this will be the natural log of z divided by z squared plus 1 dz. So we'll evaluate this integral. So the integral over the small loop of the natural log of z divided by z squared plus 1 dz. We have to parameterize this, so we can let z equal epsilon e to the I theta. That means that dz is I epsilon e to the I theta, and that theta ranges from pi to 0. So it's equal to the integral from pi to 0 of the natural log of epsilon e to the I theta over z squared, which is epsilon squared e to the 2I theta plus 1 dz is just I epsilon e to the I theta d theta. And as epsilon approaches 0, this will go to 0. We're just left with the integral from pi to 0 times I of the natural log of epsilon e to the I theta times epsilon e to the I theta d theta. So we have I integral from pi to 0. We can use logarithm rules to expand this as the natural log of epsilon plus I theta epsilon e to the I theta d theta. You can combine this into two integrals. I, the integral from pi to 0, the natural log of epsilon times epsilon e to the I theta plus I integral from pi to 0 of I theta times epsilon e to the I theta. And the limit as epsilon approaches 0, this entire integral goes to 0. And we're left with the integral from pi to 0 of I e to the I theta times the limit as epsilon approaches 0 of epsilon, natural log of epsilon. And we will focus on this limit. So this is the limit as epsilon approaches 0 of the natural log of epsilon over 1 over epsilon. We can use L'Hopital's rule to have 1 over epsilon over minus 1 over epsilon squared. And this will become the limit as epsilon approaches 0 of minus epsilon, but that clearly goes to 0. So if this is 0, then this entire thing is 0. So that means that the integral of the small loop is equal to 0. So that means we have the integral over a contour is I pi squared over 2 plus 2I. So now we just have to evaluate this contour integral. So the integral over this contour of the natural log of z divided by z squared plus 1 dz, we said there's a pole at z equals I, and we use z equals I because it's inside our contour. So we can use Cauchy's residue theorem. This will be 2 pi I, the residue at z equals I, of the natural log of z divided by z squared plus 1 is equal to 2 pi I, the residue at z equals I of the natural log of z, and z squared plus 1 can be factored as z plus I times z minus I. So this will be 2 pi I, the limit as z approaches I of z minus I, natural log of z, divided by z plus I times z minus I. So these go away. We're left with 2 pi I, the limit as z approaches I of the natural log of z divided by z plus I. So we have 2 pi I times natural log of I over 2I, and these two's cancel. This I cancels, and we're left with pi natural log of I, and the natural log of I is I pi over 2, which just I pi squared over 2, which is the value of this contour integral. So we said the contour integral was I pi squared over 2 plus 2I, but that means that I pi squared over 2 equals I pi squared over 2 plus 2I, and we just have to solve for I, which is our goal integral. So we have I pi squared over 2 minus I pi squared over 2 equals 2 times I, but this clearly goes to 0 when we just have 2I equals 0, which means that I equals 0 over 2, which means that I equals 0. So we can say, therefore, the integral from 0 to infinity of the natural log of x divided by x squared plus 1 dx is just 0. And this is the final result. Thank you very much for watching.